You know, most of us find that when we're faced with a problem of this magnitude, it leaves us feeling almost overwhelmed and numb. And I think it's terribly important that we get some understanding of a way ahead that can see us through the crisis with some realistic degree of hope. So, Bo, I don't know if it'd be in order this morning, but I would like to bring to you the best shot we have at a possible solution to go through this crisis and to begin to look at the way ahead rather than just leave you hanging on the end. Would that be okay? Yeah, I know I'm stepping over my time limits, but I really feel that this could be quite important for our whole process together. Thank you. Okay, I'll do that, and I will be as brief and sharp as I can be. Let's have a go. We've seen the reality for what it is. We've turned round on the lip of the Victoria Falls and seen the abyss below. Now, what do we do? How do we get back into safe water? Well, we're going to start by looking at the whole concept of the heat engine, the radiative forcing that is driving the problem. Global heating is the gap between the energy received from the sun and the energy radiated back into space, normally held in equilibrium because of our intervention, significantly out of kilter. So it's been behaving like this. The energy driving global warming has been accelerating, actually more than exponentially. That's our problem. Where does it come from? From a series of greenhouse gases. The carbon dioxide particularly has made the most difference. We measure the heat engine in terms of watts per square meter on the Earth's surface. So carbon dioxide has added about 1.5 watts per square meter to the heating. Methane has added about 0.8. The nitrous oxides from fertilizer use have added some. The chlorofluorocarbons, the ones that attack the ozone hole, have added some as well. But they've stopped growing from the success of the Montreal Protocol that limited their use. They stay up there an awful long time. So by 2000, we had about 2.5 watts per square meter from the greenhouse effect. And here's Jim Hansen's updating of that in 2005. And you'll see there's that 1.5 watts from carbon dioxide, 0.5 watt from methane, some from the chlorofluorocarbons. Can you say chlorofluorocarbons quickly with your false teeth in? I couldn't. Ozone, low-level ozone, basically from transport, gives more than the chlorofluorocarbons. Oh, and black carbon, sooty particles in the atmosphere, warm the atmosphere. They also settle on snow and ice and decrease the amount of light that is reflected back from them. So black carbon is adding a significant amount to the heating. And then there's the reflection from particulates in the atmosphere, what we call global dimming, with the double effect, both from the particulates themselves and the clouds that they lead to formation. So we have about just over 2 watts dimming from that effect. A little bit of change from change in sun's activity during the period from 1750 to 2000. A little bit of increase in sun. But in fact, did you know that the solar output, the energy we receive from the sun, has decreased since 1987, when most of the global warming has occurred? So keep that in your mind when people say it's all to do with the sun's radiation. By the way, if we add these last 5 elements together, the black carbon, the aerosols, global dimming, and the solar activity, that's about -1 watt per square meter. You put that into the memory bank and hold it for a minute. Historically, right, we have virtually no change in global heating. It stays at 0 up to the point of the onset of the Industrial Revolution. By 2000, there's that carbon dioxide gone to 1.5 watts per square meter. Bring it up to date, that's up to 2007, it's slightly more today. We can add on the effects of the other greenhouse gases. Then we have to add in the effect of water vapor feedback. Water vapor is a very powerful greenhouse gas, which we tend to ignore most of the time. It accounts for about half of the greenhouse effect. But when temperature starts to rise, water vapor in the atmosphere increases, and that accelerates the rate of heating. Water vapor adds about 1 watt per square meter per 1 degree rise in temperature. So we've had about 0.8 of a degree rise in temperature, so that's an extra 0.8 of a watt per square meter. And then we add on a little bit extra for the change in the albedo effect, the reflection from ice and snow. As the ice fields have shrunk, the snow fields have shrunk and lasted less time. So that's about 4 watts per square meter. It's not a lot, you say? Not a lot. We have to take off from the memory bank brought in 1 watt per square meter from global dimming. And by the way, as the temperature increases, we radiate more into space, so that decreases the heat engine. We've just been able to do the first calculations of that, so we're taking off another watt for our current temperature rise. That gives us about 2 watts per square meter of the heat engine. I don't think watts per square meter mean very much to you. But tonight we have the final of the European Football Cup with Spain against Germany. The results will be interesting to see. But there's about the equivalent of 8 kilowatt fires on the football pitch, which you'll be seeing tonight. Add that up to a global total, and you're looking at about 1 million gigawatts. Mind-blowing numbers, aren't they? 1 million gigawatts over the whole Earth. Or if you want to put that into kilowatt fires again, that's a trillion, 1 million kilowatt fires. That's some heating. You know, sometimes somebody just absolutely deflates your bubble in a presentation like this. Somebody once said to me, you know, they're not using kilowatt fires anymore, it's all central heating. And I said, oh, for goodness sake, I have to think of something else. But this will do for now. Gives you an idea. Oh, by the way, the heating is increasing by about 25% per decade. Oh, and that rate of increase is increasing. Climate stabilization means reducing that heating to 0.